Chapter 7. I'll get the homework up tonight. I haven't got to it yet, though. Okay. So we're going to talk about random variables. So random variables, these are variables whose outcomes are determined by probability. So the idea is, you could call, say, a random variable x to be, the number of heads and 10 flips, right? So the number of heads you could see in 10 flips, you could see none or 1 or 2 or 7 or 10. And those outcomes are all determined by chance. Some of those outcomes are more likely than others, okay? If you called y would be, say, the height of CBC male, right? That's a random variable. Every time you look at somebody, every time you take a sample, you're going to get someone of a slightly different height, but some heights are more likely than others, right? Okay, so it just means it's some variable. It changes, but it doesn't change without any pattern. It changes based on probability, like flipping of coins. All right. So these are random variables. We're going to only deal with quantitative random variables from this point on. We're not going to look so much at categorical as much. Okay. So remember, we have these properties of probabilities, right? So if you have some random variable and you have a bunch of outcomes and you have a bunch of probabilities, right? Then what were the rules about probabilities? There was basically two rules about probabilities. What had to be true? Yeah, one of the rules is that if you added up all the probabilities, they had to come out to 1. Otherwise, you didn't actually have like a valid probability distribution. That was one of the properties. What was the other property? That probabilities are always between what? 0 and 1. Right? Now, when we were looking at events and probabilities before, though, we had like a discrete number of outcomes. Like you could only have 1 or 2, or we had categories. Okay? So what I want to look at now, though, is what happens when we're not dealing with like categories or discrete variables. What happens when we start working with continuous random variables, right? So there's two types of variables. You have the discrete and you have continuous. What's the difference between discrete variables and continuous variables?
Discrete is fixed values.
Yeah, so discrete is usually like counting values, like you can have 1 or 2 or 3 or 5 of them. But I want to focus on continuous. Now there's a problem, though, with continuous random variables, because with continuous random variables, if you try to make a table for a continuous random variable, you run into trouble really fast, right? Because if I try to make a table with a continuous random variable, let's say I'm talking about the heights of males, right? And I start my table. I don't even know where you would start the table at, but let's say we're in inches. Then you might start the table at 50.0 inches, but then someone could also be like 50.01 inches, or they could be 50.001 inches, or they could be 50.0001 inches. You get the problem, right? And they could be 50.02 inches, or 50.002 inches. So I'm going to be listing like a bajillion heights before I even get to 51 inches tall, right? My table's going to be huge. And so for a continuous random variable, because we measure it on those fine intervals, hundredths, thousandths, 10,000ths, we can't really construct a table with probabilities, because we'll have, if we were to observe like CBC students, you know, I could come up with like, you know, 1 million different heights, and there's only like 4,000, 3,000 guys here. So I'm going to have a bunch of heights that have 0 probability and a bunch of heights that have like one, you know, 4,000ths of a probability. So it's a problem. So we can't do tables with continuous random variables. So what we can use, though, is we use things called density curves. All right. So a density curve we've actually seen before is a normal distribution. Okay. So the curve itself is what we call a density curve. All right. So that nice bell-shaped curve. Over here, you know, you might have, this is like x and probability of x. And a couple things about density curves is that when the curve is taller, that means you're at a place where you're more likely to see the random variable, right? So the taller the curve, the more likely you are to see things in that general vicinity. The other thing is to keep it analogous with the tables, like before all of the probabilities had to add up to 1. In a density curve, we fix them so that the area under the curve is equal to 1. All right, so it's like if you were able to actually measure the area under this whole curve, the area under that curve would be 1. So we're kind of serving the same purpose. In the table, wherever your numbers were bigger, those were more likely events. In the density curve, wherever it's taller, they're more likely events. In the table, the probabilities had to add up to 1. In the density curve, the area has to add up to 1. And if you want to calculate probabilities, so if you want to calculate the probability that, say, a continuous random variable is between 2 points, say like A and B, then it's going to be the area under the curve between A and B. Okay? So with continuous random variables, because we can't possibly table an infinite number of outcomes, we use a density curve that rises where it's more likely, has an area of 1, and then we can calculate probabilities associated with it by calculating areas under that curve between 2 points. Okay? So this is going to be the idea. And we actually kind of did something similar to this back in chapter something, 3-ish. You remember we talked about the normal distribution and we talked about a rule. Do you remember what that rule was? That had to do with calculating percentages or probabilities with a normal. What was it? Remember that one? Right? And we said that if you're at a normal distribution with a mean, if you go out to 1 standard deviation, what have you covered about?
68%.
You cover 68% of a normal distribution. And actually what that corresponds to, that actually tells you that the area under the in this region is 0.68. Okay. And if you went out another one, right? You go out 2 standard deviations. What was true? That's where you covered 95%, right? So if you were to go out 2 standard deviations, at that point, you will have covered 95%. In the area under that curve would be 0.95. Okay? So the areas are equal to probabilities or percentages under these curves. And this is true typically for any normal distribution. All right, so we kind of dealt that. I'll give you a brief reminder of how we use that. So here's an example. So if you look at serum total cholesterol levels, they take on about a normal distribution. The mean is 180. The standard deviation is 36.2. So what's the probability that if you randomly select a male that his cholesterol exceeds 216.2, right? So if you remember how we did this, we drew out the distribution. So it's centered at 180. Okay. If you go up one standard deviation, what does that take you to? Well, it takes you to exactly 216.2, right? And I'm interested in the probability of being above that. So how did we solve a problem like this before? Divide what by 2? That's true. Is it? Well, what's the, okay, so you go down a standard deviation. This would be 140 something, 5.8. What percent is in this area? 68% is within one standard deviation mean. So how much is here and how much is here? Yeah, so that means this must be 0.34 and this must be 0.34. So then what does this area up here have to be? Has to be 0.16. Why? Yeah, so if you think about it, remember the symmetry of the normal distribution, right? Well, how much is above the mean? 50% is above the mean, and then you take away the 34% that we already covered, and what do you end up with is 0.16. Yeah. So there's the probability, there's a 16% chance that his cholesterol exceeds 216.2. Right? Okay. All right. So that's, was that chapter 3 or 4? I can't remember. It's not that important. I think it was 3. But anyways, so we kind of used this concept already where you have a density curve and you have areas underneath it and they correspond with probabilities. Just before when we did it, I didn't specifically mention to you that this is in fact the area under the curve between those 2 points. So actually, if you were to actually measure this, the area of that little chunk right there is actually 0.16, or about. The empirical rule is approximate, but it's about 0.16. Okay. So that's really nice and convenient. If our observations happen to fall exactly on standard deviation markers, unfortunately though, typically that's not really the case. We're not typically interested in limiting ourselves. Okay. So a lot of times it doesn't work. Okay. So, for example, what if I just wanted to know what's the probability that a cholesterol level of a randomly selected male exceeds 200? Okay, not 216.2. So here's the distribution. You know, it's centered at 180. The standard deviation is 36.2, so this was 216.2. But where is 200 at? Where is 200 at? About, I don't know, halfway between them. You know, 200 is like right here. Well, if I want to know the probability, so if I want to know the probability that x is greater than 200, I need to know the area above 200. Well, what do we do? If all we have is a 68, 95, 99, 7 rule, then what are we going to do? Could we guess it? Could we at least bound it? Could we at least have like a boundary on it? It has to be between this and this. Is it going to be more than 16% or less than 16%? More, right? Because the probability of being above 216.2 was 16%, and this is obviously more than that because there's more. Is it going to be more than 50% or less than 50%? Less, because above the mean is 50%, and this is less than above the mean, right? So it's somewhere between 16% and 50%, and I mean, so we know that. That's all we can really say, though, at this point. It's somewhere between 0.16 and 0.50, and honestly, I just don't really know anything beyond that without taking kind of just a wild stab in the dark. So we're not going to do that. We're going to come up with a better way to do this. So this is the question we want to answer now, is how do we find probabilities with normal distributions when we can't use the empirical rule? All right? So we will need to go back to that thing we called the Z-score, right? So what was the Z-score? That was the IQR, the interquartile range, but it was something. It wasn't the Z-score something else, though.
Oh, it's the mu over sigma.
It has to do with a mu and a sigma, right?
Mu and the sigma.
Yeah, what is mu?
The mean.
The mean. What is sigma?
The sum of all.
Standard deviation. Are these, if you write them as mu and sigma, are these population parameters or sample statistics? These are population parameters, right? So mu and sigma are the population notations. If we wanted sample, we would talk about x bar and s, right? Okay, so for a z-score, if you have an observation, so if you have an observation x, okay, then its z-score is what? You take the observation minus the mean over the standard deviation, right? That's how you calculate z-scores. And what do z-scores tell us, or what do they help us see or learn about an observation? It's not an average necessarily. How far an observation is from the mean in terms of its what?
Standard deviation.
Yeah. So it's a measure of relative standing, right? And it tells us how far above or below x is from the mean. Okay? All right. Cool. So here we go. So we got this z-score. It's telling us how far things are above the mean, below the mean. And now, why is that useful for us? What we're going to do here is, for this particular, okay, so let's look at the male first, right? So let's look at a male with the cholesterol level of 200, right? So if I was just, remember the mean of their cholesterol levels was 180. The standard deviation was, what was it, 36.2, right? So then the z-score is x minus mu over sigma. So what's our observation right here for this person? What goes where? Yeah, so if you randomly select a male, his cholesterol is 200, you would take observation minus the mean over the standard deviation, right? So that would be 20 over 36.2, which would come out to something. Let's round it to 2 decimal places. 0.55? If you round it to 2. Yeah. Okay. So this person is a little more than half a standard deviation above average in terms of their cholesterol level. Okay, but that still doesn't answer our question because I still don't know. I still don't know this probability, right? I know they're above average. I know they're about a half a standard deviation above average, but I don't know how likely it is to be up there in that area. Like how likely is it to find a man that's up in that range? So what we need for this is something called the Z-table. All right, so what I want to show you here, I have some data from from StatCrunch here that I want to show you. Go back here. I got the e-text up too. Data sets. Nah, just go to the website. Okay, so for example, here's a data set where they had measured the heights of 5-year-old females in a health clinic. All right, and what I want to do is at first I just want to look at a graph here. So if I were to graph these heights of 5-year-olds, what does it look like? Looks pretty normal, right? Nice normal distributions. Heights typically have nice normal distributions, so this is pretty. We're not surprised by this. What I want to do is I want to calculate the mean and standard deviation of these. So remember, we can do that summary stats for columns. For them, all I want is the mean and the standard deviation. Okay, and actually, I'm going to treat these like the population. So I'm going to do the unadjusted standard deviation because I'm going to assume that this is like all of the 5-year-old females at this clinic. So we'll go ahead and say, okay, so here's our mean and here's our standard deviation. So 42.22, 3.11. I want to remember those. Somebody write those down. The mean is 42.22. The standard deviation is 3.11. Yeah, somebody wrote those down? Perfect. Okay, here's what I'm going to do. What I want to do is now I want to calculate the Z-score for all of these 5-year-old females. So what I can do is it I think it's in data actually. What is it? Compute. There we go. Here's what I want to do. I want to take, so what I'm going to do is I'm going to build their Z-scores. So I'm going to take everyone's height. I'm going to subtract off the mean, which was what, 42.22, and I'm going to divide by the standard deviation, which was 3. Why am I? Whoa. Yeah, 3.11. Okay. I don't know what just happened. Okay, divide by 3.11. Okay, and I'm going to call this Z-scores for heights. Boom. Okay. So it just went ahead and calculated them all at once. So so this person right here, this girl was 44.5 inches tall. So she was 0.73 standard deviations above average, right? This girl right here was 39.6 inches tall. So she was almost 1 standard deviation below average. You see what I mean? Okay, so these are all their Z-scores. So it's just this minus the mean over standard deviation. And you can see some of the Z-scores are negative, some of them are positive. That's because some of them are above average, some are below. What I want to do, though, is I want to look at the histogram. I want to see what those Z-scores look like. So here is the original distribution. Here's all their Z-scores. And I want to put them, let's put them side by side. Columns would be 2. Boom. What are the what's the shape of the Z-scores? Think so? Maybe a little. Not much. As a statistician, I would say that's pretty good, actually. You know, that's pretty symmetrical. It's pretty normal. But what else do you notice about the Z-scores? How are these distributions the same, and how are they different? I think they're both normal. So that's how they're the same. How are they different, though? What's that? Yeah, there's something about the way they split up for some reason, StatCrunch decided to split up they did their bins differently. That's just the computer automatically generates those. Has to do with the range, but what else? How are they different?
Are they mirror images?
They almost look like it, don't they? Yeah, I think that's Yeah, that's weird. Actually, I think that's coincidental, but they do almost look like mirror images. That's true. Yeah. So I'm not okay. So don't focus on the shape. I'm not interested in the shape so much. I think to me, as someone who's looked at a lot of data, both of these look about as normal as you're ever going to get. So the shape are essentially identical. They're both normally distributed, but what's different? So I'm not focused on the shape. The z-scores start higher? Here, let me read you these. Don't look at the frequency. I want to look at relative frequency. Oh. Okay. All right. So, how are they different?
Can you give us a hint?
I want you to get creative.
3 and then we'll go to 0, 2.
So the relative frequency, but that's really has to do with the way the bars are split. I could probably change that. Well, I can't because I got two different data sets. I wish I could. I can't fix their the number of bins, so I can't change that. StatCrunch just defaults to that. So. You're right. I mean, they go up to sort of relatively different frequencies, but that's just because of the way they split their bins. So, how else are they different? The bottom numbers are different. Well, if you look at the just the raw heights, what is that distribution? Where's the middle of that distribution? Where's the middle of this distribution at? It's at what? I don't see a 65 on there. Yeah, it's right around 42, 43. Well, what's the actual mean of these data sets? What's the actual mean? We calculate, right? Yeah, 42.2, that's right about here, which is pretty much exactly the middle of this distribution. But what are z-scores centered around? Yeah, z-scores are all centered around 0. Does that make sense? Does it make sense that they be centered around 0? Some say no. It does make sense, but I want to know why. Why would it make sense that the z-scores would be centered around 0? Well, so some people are going to be above average. They'll have positive z-scores. Some people are going to be below average. They're going to have negative z-scores. Some people are going to be right around average. They're going to have small z-scores, right? So why is the center of the z-scores at 0? Hold that thought. What were you going to say?
Because it measures how far 60% is above average.
How far above average?
In units.
Mm-hmm.
It's above, like, 1% is above 1 unit above average.
Yeah, so the z-score is measuring how many units, like in standard deviations above average, like 1 unit above average, 2 units above average, or 3 units above average? Or potentially 1 unit below 1 unit. What about the mean itself? What's the z-score of someone who's exactly average height? What's their z-score? Someone said it. 0, right? If your height is 42.2 inches tall, and you're one of these girls, what's your z-score? 0, right? So if the original distribution is centered around the mean, then the z-score should be centered right around 0, because the mean has a z-score of 0. Okay, so this is not. I'm not just doing this for fun. This is important because it turns out this is always true. It doesn't actually matter what normal distribution you start with. If you calculate the z-scores are always going to be centered at 0, and it looks like they have a standard deviation of about 1. This is always true. Okay? So the z distribution, okay, is this distribution that's centered around 0 with standard deviation 1. So let me put that here. Okay. So this does it automatically. Nice. So there's the Z distribution. Call it the Z distribution. Okay, it's a normal distribution. With a mean of 0 and a standard deviation of 1. Okay, so it's a really special type of normal distribution. Sometimes you'll hear it called standard normal. Okay, so there's infinitely many normal distributions, right? A normal distribution can have any mean and any standard deviation. But what we've realized is, okay, but if you start calculating z-scores, all these normal distributions start looking the same. They all start looking like the standard normal distribution or the z distribution. So what somebody did a long time ago, statisticians did a long time ago before we had nice computers, really handy, is we created this thing called the Z-table. Okay. So if you go to the textbook, I'll put these out for the test. You can also open them from your homework. It's going to be back in the appendix. I'll show you what a Z-table looks like. Boom, boom. Okay, so here's our table of random numbers. That was fun. Remember those? I taught you how to read them wrong. That was cool. What the heck is this? Oh, there's something we don't need to worry about. Where is it at? It's back here somewhere. There's A5. There's A. What's going on here? Ooh. Yeah. Z-table. Come on, where are you? I'm gonna get to it eventually. What are all these tables? Here you go. Here's a Z-table. Here's what a Z-table shows you. Okay. What a Z-table does is it calculates the area under the curve for a bunch of different Z values. Okay. So the way you read a Z-table is you have a Z-score that's rounded to 2 decimal places. The column shows you the Z-score to the first decimal, and the row up here shows you the second decimal of the Z-score. Okay, so if I wanted to calculate the area or the probability of being less than, say, like negative 2.93, I would go down to negative 2.9. This would be negative 2.90, 2.91, 2.92, 2.93. And it would tell me that the area below negative 2.9 would be 0.0017. Pretty low. Should be pretty low because that's a pretty low Z-score. And notice as the Z-scores get bigger, what happens all the way up to a Z-score of 0.0? What's the probability of being less than a Z-score of 0? 50%. Makes sense because it's centered at 0, so the probability of being below 0 better be 50% because it's symmetric. Okay? So what we can do is we can actually calculate probabilities. If we know a Z-score, we can actually calculate probabilities associated with it just by using the normal, the Z-table. And there's 2 sides to the table because you can have negative Z-scores and you can also have positive Z-scores, right? So the other side of the table is positive Z-scores. Now notice it always measures the area below. Okay? So it's always measuring the area below that Z-score on the normal distribution. So let me show you how it works. I'll do a couple examples here. Okay, that's the wrong PowerPoint. Don't save that. Okay, forget about that. We're going to do some practice with the table first. So let's say that I wanted to calculate the probability on a Z distribution or standard normal distribution. What's the probability that you see a Z-score less than negative 1.52? So we're out here on the Z-table centered at 0. Is negative 1.52, it's going to be down here, right? Negative 1.52, and I'm looking for this area. Okay. That's what we're looking for. So we go to our table. It's a negative Z-score. So I need to be on the negative side of the table. I go down to negative 1.5 on the columns, so negative 1.5. So then this would be negative 1.50, 1.51, 1.52. And this is what I'm looking for. And I don't know if you can read it or not, but it says 0.0643. 0.0643. So that would be the answer for that one. 0.0. So this area here is 0.0. What did I just say? 643. 643, which means that the probability, if you just randomly select something off of this distribution, the probability that you get a z-score down there is 0.0643. So there's about a 6%, a little more than a 6% chance that you're going to see things down there. Not super likely. Not super likely. All right. What about the probability of being greater than negative 0.36? So here's negative 0.36, and I want greater than, right? So that means I actually want this stuff up here, right? It's supposed to be a negative. Okay. So what are we gonna do? I want the probability above. So first I need to go look up my z-score. So negative 0.36. So we'll go over here. So negative 0.3. I'll pull it up for you. Negative 0.3. This would be 30, 31, 32, 33, 34, 35, 36, and it's right here. And if you can't see it, it's 35.3594. 0.3594. 0.3954. So this, now the thing is though, is where is that area? Remember the Z table always reads below. So the table told me that area down there was 0.3954. So then what has to be the area above that? Yeah, so remember, since the whole area has to be 1 under the curve, these are like complements basically, right? Being below is the complement of being above, so we can do 1 minus 0.3954, and that would give us 0.6046, I think. 3954, yeah. Was it 3594? 3954. Did I get it reversed? Oh, boom. Oh, yeah, so I got it backwards. 0.30123456 3594. Dang it. That's okay. Easy fix. 3594. 3594, which would change this to 6406. So 0.6406. Is that true? Yeah. So I think that's your answer. All right. Okay, so you take your z-score. The first 2 decimal places go down the column. You look up the second decimal place by the row. I'm gonna have to make sure to bring my z-tables tomorrow. What if you wanted to do an in-between probability? So I'm looking at my z-distribution, centered at 0. Here's 0.46. Here's negative 2.03. And I want to go in between. So how do you do something like that? Any ideas how we could find that number?
You can find the 2 tails and the left and then subtract them.
Yeah, so what we could do is we could maybe use this probability down here in the tail. Because what we could look up here is, say here's 0.46. Could I look up that probability in the table? Sure. And here's negative 2.03. Could I look up that probability in the table? Sure. And then what would I have to do with those 2 probabilities to get the one I'm interested in? Yeah, because notice between what I really want is I want everything below 0.46, but then just subtract out everything below negative 2.03. That'll give me what's left here. Okay, so we need to look up 2 probabilities here. I need to go get the probability of 0.46. So that's going to be on my positive side of the table. 0.4, 0, 1, 2, 3, 4, 5, 6. So that's 0.6772. So this one is 0.6772. And then I'm going to go get this tiny tail probability down at the bottom. That's going to come on the negative side of my z-table. So negative 2.0, pull it down a little so you can see it better. Negative 2.0123, and that's 0.0212. So this is 0.0212. All right. So when you get home, you should pull up that table and see if you can make sure you can get these numbers off of it. All right, then all I need to do then is I need to take that bigger number. So then this area should be the big area minus that tail I don't want. And that'll give us our answer. So that'd be what, 0.6560? I think would be your answer. All right. All right. So I'll put up some homework tonight. Go log on to your, if you open up your text, you can scroll back to those appendices and see if you can find those values that I was pulling off the table yourself. I'll bring some copies of a Z-table though. Hopefully I'll remember to do that tomorrow. So it's in my